This is section 16.5, Curl and Divergence. The idea here is that we've been looking at these vector fields F, and we want to learn a couple of operations we can do on these things and how to interpret those operations. We're going to see these come back a little bit later. You might have noticed we were jumping from 16.1 to 16.5. That's true, so it's not going to affect the continuity of the lesson at all. I think this stuff is a perfect fit for where we're at in the course, and it'll weave back in a little bit later. So let's jump in here. Let's first, these are two different operations we're talking about doing to vector fields. Let's first talk about curl. So I've got a definition here. If F is the vector field PQR, so component functions P, Q, and R, if F has those component functions and is a vector field on R3, and the partial derivatives of P, Q, and R all exist, so you can take the derivatives of these things, then the curl of F is the vector field on R3 given by this expression down here. So the curl of this vector field is yet another vector field we define this way. It is Ry minus Qz, Pz minus Rx, Qx minus Py, right? This is just subscript notation for partial derivatives here. Partial of R with respect to Y minus partial of Q with respect to Z, and so on. So this is denoted curl of F as I've written here. We'll talk about what this means, what this operation tells us about a vector field or gives us about a vector field. But first, let's note what I've written down here at the bottom, that we can also actually write, and it is common to write, the curl as this del cross F. And so I want us to remember what that del really represented. We said to think of it as a vector. This is our del. Think of it as a vector full of partial derivative operators. They're not actually the derivatives themselves. They're the operation that will produce a derivative when applied to some scalar function of x, y, and z. So that's how we thought of that del vector. Now, what would it mean to take a cross product of this with F? Well, we have to take a look here. Oops, we don't need to go through determinants. We already know this. All right, all we're going to do is set this up to show that this is actually pretty consistent to use this expression, del cross F, for the curl of F. Let's actually compute what this would look like if we crossed the del vector with this field F PQ that equals PQR, right? Just a general field PQR. Well, then we're just treating this like a cross product between two vectors. Right, we know a little bit about cross products. The del vector will go in the second row. And finally, the F field, its component functions will go in the last row. Right, you're just filling up a usual cross product here, but you're filling it with sort of strange objects. So let's see what we get in the I direction. We're going to get, let me even write it this way. In the I direction, we get the 2x2 determinant of this stuff. The J direction always gets that extra negative. We remember that. And what's left behind when we cross out the row and column of J is this. And finally, when we cross out the row and column of K, we get this 2x2 determinant. And so if we just follow our nose and compute this out, we're getting in the I direction, we're getting d partial with respect to y applied to r minus partial with respect to z applied to q. Notice that's just ry minus qz. That's exactly what we said the first component, the I component of the curl should come out to, ry minus qz. Let's see what we get in the j. Well, by computing out this 2 by 2 determinant here, I get Rx minus, I want to be clear, when we say we're doing a determinant, we're not really multiplying this operator on this function R, or multiplying this operator partial with respect to z on this function p. We're just placing it where multiplication would appear to place it, right? If we were going through your usual determinant, visually it ends up looking like this, but we know we're not really multiplying by an operator. We're applying it. We're taking this operation of R. It's not multiplication, though. There's no such thing as multiplying. Well, I suppose there could be, but this is not multiplying an operator by a function. It's applying the operation to the function. So we think of these things very as memory devices, right? It's not actually multiplication here, but it follows the same sort of visual pattern that usual determinants and multiplication in those would appear to look like. So in this last one, it looks like I get, just going through it, we're seeing at the end of the day, in the I direction, we got Ry minus Qz, right? So we put that in the first component. In the J direction, that's the second component, we got Rx minus Pz, but remember the negative out front makes that Pz minus Rx. Oh, that saved the day. That matches our second component in the definition. And finally, back here, Qx minus Py in the K. So this is how we're actually going to compute curls. We're not going to memorize this formula. You could, but I wouldn't recommend it. Don't memorize this formula. Memorize it's the cross product of del with f. Memorize that it's del cross f. That's why it's very useful and common to represent this with this notation, del cross f, because the notation itself tells you how it's computed, right? You just remember what a cross product is and what a del vector looks like, and there you go. So anyway, we will, when we're computing these curls, we're actually going to compute using these 3 by 3 determinants, not by just memorizing a formula and calculating all the parts and plugging it in. So let's see that here with this example. Find the curl of this field, xy in the I direction, yz in the j, and zx in the k direction. Well, curl of this field, remember we kind of want to think of it as the del vector crossed with f. So this isn't bad. We just set up the cross product. Maybe for these we use shorthand. I'll do this instead of the full partial with respect to x. I'll just write that little delta x there. And in the last, we're going to take the components of f. In the last row, x, y, y, z, and z. I'll write this in the right order. X, z. Let's put that z last. And we're just taking the 2 by 2 determinant of this stuff. When I do that in the I direction, I get partial with respect to y applied to xz, that's 0. Partial with respect to z applied to yz, that's minus y. In the j direction, put that negative out front, I get partial with respect to x of xz, that's z, minus partial with respect to z of xy, that's 0. Finish up in the k direction. It looks like in the k direction I get partial with respect to x of yz, 0, minus partial with respect to y of xy, which is x. So it looks like the vector we get at the end of the day is this vector. Notice there's some sort of symmetry in this function, kind of translated through to this. Nice pattern between the components. Nice pattern between the components. Anyway, that's how we actually compute these things. Now, if I wanted the curl at a specific point, like the curl at the point 1, 1, 1, that's a point in the domain. All I'm doing is plugging that in, and I get this vector. Oops, the curl at 1, 1, 1. Right? This is a function. This is a field. You can plug in any point in the domain into that field and get an actual vector out of a numerical vector out. So let's look at another fact here, a theorem. This is a very important one for us. We'll see this come up in this whole idea of this theorem being very important. So important, I'm going to put a star somewhere. How about here? I'm going to say this is an important one to remember. This says, if f is a function of three variables with continuous second partial derivatives. So we're thinking of a scalar function of three variables. Something like that, right? Then the curl of its gradient is the zero vector. And I've written down here just another phrasing of this. In other words, if the field is if you have a conservative field, capital F, then, and it's conservative, right? Then the curl of it has to be zero, right? Because if F is conservative, then there exists little f such that the gradient of little f equals the field. Well, that just means the curl of the field is the curl of that gradient. And according to what we set up here, the curl of a gradient has to be zero. So that tells us, yeah, the curl would be the zero vector. The curl would be the zero vector if the field is conservative. Okay, so this is actually not too bad to prove this fact. All you have to do is remember what this is saying. It's like we're saying our field that we're plugging in is the field filled with fx, fy, and fz. So if we go back up here, right, this is like our p, q, and r components. So if we go back up here to the formula, think of plugging in p equals, or the field, if it was our gradient field that we were taking a curl of, then we would have these components taking the place of p, q, and r in this formula. So let me replace those. If I had instead of ry, if r was replaced with fz, I take a y derivative, that's what I'd have there. And here qz would be, well, q is fy now, so minus fyz. But notice these are just the same second partials, the mixed partials, in opposite order, right? fzy and fyz. By Clairaut's theorem, if these second partials are continuous, where were we? Yeah, here. If the second partials are continuous, then Clairaut's theorem applies. And up here, when we plug those in, we just got the same thing minus itself is zero in the first component. If we do the same sort of thing to the second component of the curl of the gradient of little f, the pz becomes, well, p is fx, that's fxz. And the rx over here, that becomes fzx. Those are the same thing, so they cancel by Clairaut's theorem, and so on. You can check it works for the last component as well. But so it's a pretty easy little theorem to prove that the curl of a gradient is always zero, which automatically follows with the fact that the curl of any conservative field is zero everywhere. So let's use that fact to show that this field is not conservative. Well, all we need to show is that the curl of this thing, the curl of f, is not identically zero, right? If that doesn't always equal the zero vector, then it certainly, up here we're saying if it is conservative, then the curl will equal zero. If it doesn't equal zero, it must not have been conservative. So we just show that the curl's not zero, it can't be conservative. So compute the curl. Takes a little bit of time. I would really recommend not rushing though. The more clearly you lay out these problems, the easier it is to get through without making big mistakes. So in the I direction, it looks like I have partial with respect to y of xc minus partial with respect to z of yz. In the j direction, it looks like I have z. Oops. Let's see. Did I make a mistake? No, okay, this is good. So in the j I get 0 minus, yeah, 0 minus z. Second guessing myself there, but I think that's good. And in the k direction, I know we've already done this one. I'm just trying to make sure I don't mess it up. In the k direction, we get 0 minus x. Right. The point is that is not identically a 3 lines mean it's not identically equal to 0. Sure, there are x, y, z that make this 0, but it's not 0 everywhere in the plane. This doesn't come out to a constant 0. It's not equal to 0 vector. That implies f is not conservative. Okay. So let's go on to another example here. Let's show that this field, sine y in the I direction, x cosine y in the j, minus sine z in the k, is conservative, and find a potential function for this field. So I want to start out here just by saying, well, if we find a potential function, that shows it's conservative, right? That's the definition of being conservative. It's conservative if it has a potential function. Little f such that the field is the gradient of this little scalar function. Okay, so I'm going to skip the first part. If I can just find a potential function, that will show that this is conservative. So if I had a reason to believe this wasn't, or if I wasn't being told that it is conservative, I might try to test out to see if it's conservative first, just by taking the curl, right? If it's 0, if it's not 0, it's not conservative, right? So you could test that out. But since I'm going to have to actually find the potential function anyway, which will implicitly prove that this thing is conservative, then I'm just going to go ahead and jump in and find that potential function. And so I want to do that by noticing the requirement here. I want to find f, the potential function, and I want this f to be so that the field here equals the gradient of little f. So equals fx, fy, fz. And really, that just implies that each one of these conditions is true. Sine y has to equal the partial of little f with respect to x. X cosine y has to equal the partial of f with respect to y. Little f with respect to y. Negative sine z has to equal the partial of f with respect to z. And so to actually find a function f that satisfies all three of these, all three conditions have to be met, we need to do some partial integration. It's not going to be so bad. What we typically do is I'll say it this way, yeah, what we can do, a systematic way, is the following. Start out with a function f of x, y, z. You don't know what it equals, but you know that its partial with respect to x has to equal sine y according to that first equation here. Integrated this on x on both sides. And what do we get? So I'm going to integrate this with respect to x on this side. Integral of sine with respect to x. With respect to x, sine y just looks like a constant. So we just get x sine y. But we also get an integration constant. But notice this is just constant with respect to our integration variable x. Well, something that's constant with respect to x just has to not have an x in it. So it can be any function of the other two variables. That's constant with respect to x. I'll say this is an integration constant with respect to, WRT, with respect to x. So now you know a little bit about the form of f. It has to have this form. It has to have x sine y plus some function that's independent of x. Well, then we use that and go to the next equation here. Now we differentiate this with respect to y, and we get x cosine y, that's that partial derivative with respect to y, plus the partial of g with respect to y. And we know from this equation up here what this has to equal. Partial of f with respect to y has to equal x cosine y. So let's replace partial f with respect to y with what it has to equal, x cosine y. We'll do that up here. The fy on the left side I'll replace with x cosine y. That guy's gone. Now I'm just copying this side on the other side. Okay. Well, now we can subtract x cosine y from both sides, and we see that this g subscript y, the partial derivative of g with respect to y, has to be 0. Well, that implies, doing integration, that this function, integrating in y, partial integration in y, integration on this side in y just gives you g of yz, but if the derivative was 0, the antiderivative is a constant. So the antiderivative, the actual function itself, should be a function that's constant with respect to y. So that is just a function, I'll call it h, of z. Right? It's independent of y, so it's just a function of z. Well, then we go back to here, and we say, okay, now I know what g of yz looks like. It's really, I'm just narrowing down what this function looks like. Now we know this g function is really not a function of y and z. It only depends on z. And we do this one more time. We integrate one more time and use this last equation. So I should say we differentiate one more time and use this last equation. Fz, according to our work here, has to equal the x sine y differentiates out. It's just the derivative of h. Since that's a one variable function, I can just call that h prime. I don't need partial derivatives on a single variable function. But that z derivative on h of z just gives us h prime. But we know what f of z has to equal. F of z has to be negative sine z. And now we integrate h prime to get what h itself is. H of z equals the integral of this side plus a true constant, right? There's only one variable allowed, and the integration constant needs to be independent of all that, right? So now we've whittled it down to a true constant here. But we're in good shape. Now we can write down our function from here. We know it's x sine y, but now we know what h of z is. H of z equals cosine of z plus a true constant. And this is a potential function for this field capital F up here, no matter the value of c that we choose, no matter the number we tack on there. Remember, we said this is kind of like an antiderivative of this field, right? The potential function is like an antiderivative in a way. We're going to get that plus a constant there. And so you might be saying, well, isn't there an easier way? And I think there is. So this is the systematic approach, right? What I would say is also useful to remember is that this might not be as hard as it seems. Let's approach it slightly differently. I'll leave my final answer there. Let's erase just a little space. So let's look at this equation again, this defining equation of our function little f that we were trying to find. All we're saying, we could just go through this more mentally. We don't have to go through all these steps so systematically. Let's erase that idea for a little bit. So we could, for example, just say, okay, I need a function whose partial with respect to x is sine y. So you might say, okay, well, I got that. That's just x sine y, right? The partial of this with respect to x is sine y. Then you say, okay, well, that's fine. Let me test it against what the next component should be. The next one says the partial with respect to y should be x cosine y. So I differentiate this up here with respect to y, and I say, yeah, this does work out. The partial with respect to y is x cosine y, so I must be on the right track. Then I test it against the last component. I say the partial of this with respect to z has to equal negative sine z. And I test that out. And I find the partial of this guy with respect to z is 0. So I say, okay, well, then something's wrong. I'm missing something from this function that was supposed to differentiate to negative sine z. Well, can I just add something that doesn't affect the x and y derivatives that I already have? Those worked out okay, but would fix this z derivative so that it comes out to negative sine z. I think, well, yeah, I could do that. I just add on cosine z. The derivative of that with respect to z is negative sine z. This other x and y stuff still just disappears in the z derivative, so that works. And the cosine z, that looks like a constant to the x and y terms, so it doesn't affect the x and y derivatives that already checked out. Right? And then you know you can add any constant to any of these, so you just put a plus c if you need that general constant included. So this is how I actually handle these. I would call this, this method we just kind of talked through, I would call this by inspection. Right? Look at the problem and just kind of take it little piece by little piece and correct as you go. That's how you want to be able to do these most of the time, but it's good to have that systematic method that we saw first too. Okay, now finally, we've kind of put it off. Let's talk about the interpretation of the curl vector. What does this thing mean? What does it tell us about a vector field when we take its curl? And we plug in some numbers, get some vectors out. But here's how we want to think of the curl. The curl of f indicates the rotational nature of the vector field. Right, so a nice way to think about this is if the vector field f is representing fluid velocity and some fluid that's flowing, then the curl of that field at any point in that fluid is just a vector pointing along the axis of rotation of the fluid at that point. So for example, in my picture down here, I'm saying this point here is xyz. The curl of f at xyz is this vector here. It is the axis around which my fluid is rotating at that point xyz. Right, this dark arrow down here, that's my fluid flowing around this axis given by the curl vector. And you might say, well, how do I know which way it points? Here it's pointing kind of up and right. Couldn't it point back here as well? and still give that same axis? Well, it could, but it's going to follow the right-hand rule. If you put your fingers on your right hand in the direction of curl them around this vector, or curl them in the direction that your fluid is flowing at the point, then your thumb will automatically point in the direction of the curl vector. So flowing around this way gives me, with my right hand rule, gives me a curl vector coming out in this direction. If I reverse the direction, I'd have to flip my right hand over to match the direction of that curl with my fingers, and that would leave my thumb pointing in the opposite direction. So this is what I mean by the direction is determined by the right hand rule. And we should mention the magnitude of that vector also has some significance. It is the rate of circulation of fluid about that axis. Right, so a big magnitude, a long vector here means it's the fluid's rotating very quickly around that axis at the point x, y, z. So I want to look at an example. Something we should acknowledge is that a curl is only truly defined for a vector field in R3 just by the sense that the way we defined it, it had 3 components to it. So you have to have 3 dimensions to even define it. But there is a way that if we look at a field like this one I'm pointing to in this example, where it equals P of just x and y in the x component and Q of just x and y in the y component and nothing in the z, then this thing is totally independent of z. It looks like just different, the same sheet of vectors repeated at every height z. And so in this way, some 3D vector fields can be viewed in the plane, because really everything interesting about this is viewable in just a single plane, the xy plane. All the other planes in 3D give you the same exact picture. So I want to think about, in a situation like that, can we think about taking a snapshot of that, just a picture in the xy plane for some fields of this form, assume it's the same in all other planes of z, and figure out whether the curl vector at the points I've marked in these pictures points into the screen, out of the screen, or equals 0. So let's see, in this part A here, if I use my fingers to rotate them in the direction that it appears this vector field is rotating, which appears to be clockwise, kind of around that point P, then it looks like my thumb will point into the screen. So the curl vector evaluated at that point P is into the screen. Again, that's by right hand rule. Notice there's clearly some rotation going on there, though. It has some rotational nature to it. It's not perfect or uniform, but clearly there's some circulation around that point in this direction. Okay, the next one, part B, is saying same sort of problem. This one's a little more complicated, though. It's saying that up at the top of this field, up in here, the vectors are bigger, and the further down we go, the smaller they get. So if I'm right here, is there any rotational nature to this? You might say, no, those are all pointing in the same direction, so no. But think about it this way. If I put, say, like a basketball right here in a stream with velocities given by these arrows, is that basketball just is it going to just translate, just move downstream, or will it rotate in this stream as well? If it's going to rotate, then there's a non-zero curl here. Now you can think if there was like fluid flowing, the fluid's flowing faster on the top side of the ball than on the bottom side of the ball. Overall, there's more force on the top than on the bottom. It's going to rotate in this direction, counterclockwise. And so if I think about that sort of rotation in this direction, curl my fingers in that direction. On my right hand, curl them in this direction, then my thumb will point out of the page for the curl vector. Finally, in part C here, notice no matter what's happening, if I do have a truly radial field like this, something that looks like it's moving, the field vectors go radially outward from the origin with supposed to be pretty much equal length in all directions, then again, think of setting a basketball here and this being fluid flowing away from this direction. Well, if it's all equal size vectors in all directions, there will be no spinning nature to this thing. It's not being pushed or pulled harder on one side of the ball than the other, so it will not spin at all. This would be zero curl. And it looks like that happens everywhere, right? This is zero everywhere in this picture. No matter where I look, the ball wouldn't be spinning no matter where I set it. In this case, where the curl is zero everywhere, oops, sorry about that, everywhere, we say when the curl is zero everywhere, we call this fluid flow irrotational. I think for obvious reasons, right? There's no rotational nature to it. Okay. So we've seen three pretty standard examples there of the different types of curl situations you might run into, and how to get a sense of what the curl might be just from looking at a picture. So finally, let's move on to divergence. Now might be a good time to take a break if you're getting a little winded here. But I'm going to keep going, so please feel free to pause and come back. The divergence is another operation we can apply to a vector field, but this one we can apply to vector fields in R3 or R2. We said technically the curl is only something in R3, so a 2D field won't work. We can't take curl of it, even though sometimes we can kind of represent a 3D field in a 2D way, we saw in the last example. Divergence is not that picky. We can take divergence of a 2D field, like PQ, or a 3D field, PQR. So if we do have one of these fields, a vector field in R3 or R2 even, and the partials of PQ and R all exist, then the divergence of that field is a scalar function denoted div of f, so divergence of f, and it equals the partial of the first component with respect to your first variable x, plus the partial of the second component with respect to second variable y, and so on down the road. What I want us to notice is another connection to this del vector, that we can write divergence, and often do write divergence, as del dot f. Let's see why this makes sense. Remember, we're thinking of the del vector as being full of these partial derivative operators. And we're thinking of this field f as being PQR with its components. Well, then del dot f, at least formally, would look like this. Notice if we take the dot product of these two, or at least set up what looks like a dot product, we'd have the partial with respect to x applied to p, plus partial with respect to y applied to q, plus with respect to z applied to r, and that is exactly px plus qy plus rz. It is the divergence. Right, so this del vector yet again is coming in handy by showing us, almost instructing us how to compute the quantity in the way that we name it. Del dot f tells us how we actually get this px plus qy plus rz formula. You dot del with f, right? You do this operation. So we're going to kind of follow a similar path here. We'll break this thing apart, play with it a little bit, see some examples, and then we'll talk about how to interpret the divergence of a vector field. But let's see that this one is actually quite a bit easier in general to handle than curl. For example, this example is asking to compute the divergence. That's a simple problem. It's the partial with respect to x of the first component plus with respect to y of the y component plus with respect to z of the z component. And so from here, these partials are simple, right? These partials are simple. We get y plus z plus x. That's our divergence. And again, this is a function, this is a scalar function of three variables. We could plug in any point x, y, z in the domain of our field and figure out what the divergence is at that point. Here I've expressed the divergence as a function that can take any point. So we saw a pretty similar theorem to this one we're about to see for curl, but now we're going to see one that's very similar for divergence. If p, q, and r all have continuous second partial derivatives, then the divergence of the curl of f, where f is this field PQR, has to be the zero scalar. This is extremely simple to prove, right? So say you've got the curl of f. Let's remember what the formula for the curl of f is. It is the curl of this field PQR is this vector, ry minus qz, pz minus rx, qx minus py. And if we take the divergence of this, it means we are just taking the partial of each component, this one with respect to x, this with respect to y, this with respect to z, and adding the results. That's what the divergence has to do. So if we do that, that's easy. The first component here with respect to x gives me ryx minus qzx. Second component here says add on pzy minus rxy. And the last component here is saying add on qxz minus pyz. Do we see any cancellation? Ryx, by Clairaut's theorem, that's the same as rxy. We know Clairaut applies because of the continuous second partials. Negative qzx cancels positive qxz, again for the same reason. Clairaut applies, Clairaut's theorem applies. And finally, these cancel. The divergence of this curl does equal 0. Easy to show. This was like how we said the curl of the gradient equaled 0 and equal to 0 vector in the last part of this section. This is a similar thing for the curl, or for the divergence. So recall this kind of kindred formula. Okay. So we did a similar example like this for the similar theorem on curl. This one for divergence says show that this field written here, f equals 2x, 3yz, negative x, z squared, is not the curl of any vector field. Well, all we have to show then is that the divergence is not 0, because if it was the curl of any vector field, it would have this form up here, and the divergence of that would have to be 0. So we just need to show, a problem like this is saying show that the divergence of this field is not identically 0. It doesn't equal the constant 0. It'll have variables in it, or non-zero constant. So let's show this. All we have to do is take the divergence, quick and easy. Remember, that's just the derivative of the first component with respect to the first variable, second with respect to the second variable, and last component differentiated with respect to the last variable. This is 2 plus 3z. What is that? Minus 2xz. Notice this is not identically 0. It's not constant equal to 0. It's not constant at all. This is not 0. Implies f is not the curl of any field. Let's say it this way to make it clear, of any field G, because if f equaled the curl of G, then the divergence of F is the divergence of the curl, which would have to equal 0 by the theorem. And we know that the divergence of RF up here did not equal 0. Okay, so not so bad. You're just showing the divergence doesn't equal 0. Now finally, let's get to this interpretation of what is the divergence telling us about a field when we take the divergence of a field. Here's my interpretation here. A description of a vector field's tendency to flow in or out of a point. That's what divergence is. It's how the field is converging or diverging away from a point in the field. So if this field represents a fluid velocity flow, fluid flow's velocity, I should say, then this gradient, this divergence, not gradient, the divergence at a point XYZ gives the net rate of fluid flowing from this point per unit volume around that point. Right. That's the idea. So if it's a negative divergence, we're saying that overall fluid is not flowing out of the point, it's flowing into the point. We call this a sink. Called a sink. There you can think about why. Think about like the drain in your kitchen sink, right? Everything, if you fill it up with water, all the fluid's going to start flowing into that sink, into that drain. Think of the drain hole as your sink point. So that point XYZ is called a sink if the divergence is negative, meaning overall, thinking of a fluid flow, the fluid's flowing into the point. If the divergence is positive, it means we are diverging away, right? It's not the negative of that, it's the positive of that. We are diverging. So we are leaving the point. In that case, we call this not a sink, but a source. Think of the faucet of your sink. Or think of maybe if you were filling a bucket with water and you took a water hose that you were filling it with and dipped the water hose that was filling it underneath the level of the water in the bucket. Right, the fluid inside the bucket is flowing, but if you think of the point where the end of the hose is inside of that fluid, certainly that fluid is flowing outward into the bucket. So I would think of that as being a source, right? Right there. Everything's leaving the point. The fluid is leaving the point, entering the area. Finally, if the divergence is everywhere equal to 0, in that case, think about it, we're not entering the field's not flowing into or out of any points. I would think of this as, and it's exactly what it's called, we call this let's see how your book actually refers to it. Okay, exactly as it should be. Incompressible. Right? Meaning, if you had a bunch of fluid flowing into a point, that would seem to compress the area. If you had a bunch of fluid flowing out of a point, that would seem to be lowering the pressure in the area or expanding the area. We're saying neither of those things are happening. This isn't compressing or expanding at all. This is incompressible flow. All right, so the last little thing I want to do here is do a similar exercise to what we did with the curl pictures. I want to look at each of these pictures and see if the point P is a sink, source, or neither. So for example, in part A here, if I'm looking at this point P, I'm trying to get a sense of, is more fluid, thinking of a fluid flow, is more fluid flowing into the point or out of the point? Well, keep in mind, things to the left of the point are flowing into it. Things to the right of the point are flowing out of it. It looks like across this point, the vectors to the left are smaller than the vectors to the right. So there's more leaving than entering. Overall, fluid value or function value, vector function value, is leaving the point. So I'd say this is a positive divergence, implying this point P is a source. In the next one here, if we take a close look here, right, what's happening here? It looks like the fluid's rotating around our point. So certainly there's some curl going on there, but does it appear that one side of this point is gaining more function than is leaving the other side anywhere? Gaining more vector arrows entering it than are leaving it. It looks, because the symmetry of this thing around the point, that wouldn't be the case. Whatever's happening on one side is happening all around it, right? I would say it looks like this is a case where we have zero divergence. So if that happened at all points, which it very well could in a spiral shape like this, depending on the magnitudes of these vectors, in that case, this could be incompressible. If the divergence is zero everywhere. It's hard to say, but I would say the idea is that at that point, there's nothing going into or out of the point. There's just things revolving around it. So this next one, I think it's maybe more obvious. All these vectors are radially kind of pointing inward at the point P. I would say that's pretty obviously a negative divergence. Arrows are not more leaving the point, they're more entering the point than anything. So I would say the divergence of our function at this point P in this case is negative. That's a sink, right? Think of these being lines showing how fluid is flowing into a sink drain, something like that. If you've done any physics, you might recognize pictures like this and think that a sink and a source might be positive or negative charges. Certainly there's that sort of interpretation to this. Maybe definitely of a more practical use than thinking of your kitchen sink. So you are thinking along the right lines if you're making connections to field lines going into a negative or positive charge or out of a negative or positive charge. Okay, so that is it for this section. In the next section, we're going to finally use these vector fields to introduce the last topic of integration, which really is the culmination of this entire course, which is line integrals. That will lead us into the big results of line integrals known as the fundamental theorem for line integrals, and hopefully Green's theorem if we have time. More on that in the next videos.